Good afternoon. Well, thank you for being here today. It's cozy here, but it's cold outside, so I think it's keep everyone warm here. My name is Quinn Lay. I'm the Department Chair of Radiation Oncology, and it's really my true great pleasure to welcome all of you to Stanford to this event. And this event is Stanford Radiation Oncology celebrating the past, present, and future. It's our 70th anniversary, and so really 70 year old we are. Yeah. So we're really thrilled to be here to introduce you some of the innovative research that have taken place in the department. So for this evening, you're going to be hearing from 4 different speakers. They have accomplished faculty within the department. And you've learned from, I think you will learn from their talk is that we have a really strong history of innovation to bring curative care for cancer, care to improve quality of life, a combination of both. And so we strive to continue to advance these care for our cancer patient. After the presentation, then we will walk you to the Cancer Center, where you can get an exclusive tour of the department. And you'll see probably one of the latest cancer fighting technology, which is the world's first ultra compact proton machine that fits in a vault. And that's actually brokered by Dr. Bill Liu, who you're going to hear about a little bit later on, put the 2 companies together to put this new system together. And we then will have an intimate reception with folks after that. And so you have the ability to talk to many of the faculty here to learn more about what's going on in their research. So because of that, we'd like to get you to the tour, get you to your food and your drinks. So we'd like not to have the Q&A question here, but actually doing more intimately during the reception. Okay, we will have a video recording for the talks, and we will share with you later on, so you can have it. So there's no need to take any notes or anything. And then with that, I'd like to introduce you to the former chair of the department, my chair when I arrived at Stanford, Dr. Richard Hoppe, who is a Henry S. Kaplan Harry Lepperson Professor of Cancer Biology. And Dr. Hoppe, as you know, has been in the forefront in the developing research for lymphoma, Hodgkin disease, cutaneous lymphoma, since he's been here since 1972. And so he's going to talk to us about the history of the Department of Radiation Oncology.
Okay, thank you, Quinn. A very brief history. And I would add my welcome to those of Quinn. It's delightful that you could all be here to hear about the special accomplishments of many of our faculty. And as Quinn said, it was a long time ago, more than 70 years ago, that Henry Kaplan was recruited to be the first chair of radiology at Stanford. And during his tenure at Stanford, he was, among notable achievements, a co-inventor of the medical linear accelerator, which was really a game changer in the management of cancer that millions of people around the world have benefited from. The original device that he invented is now at the Smithsonian. It's celebrating its 70th anniversary, but its legacy is extensive, and its progeny are present in all of the cancer centers around the world. Together with Saul Rosenberg, whom he recruited to Stanford, Kaplan developed curative treatments for Hodgkin's disease and many of the other lymphomas. He attracted world-class scientists to Stanford, establishing Stanford as one of the leading research universities in the world. He established a cancer biology research program, which was the forerunner of many of the laboratory programs that you'll hear about today. Malcolm Bagshaw, who worked with Kaplan and succeeded him as chair of the department, explored the ways to take advantage of the linear accelerator technology. For example, He was the first to use radiation therapy aggressively in the treatment of prostate cancer. And now prostate cancer has become a major modality for which radiation therapy is effective. In fact, it has supplanted surgery as the most commonly used modality for initiation of treatment of prostate cancer. Malcolm also made our first foray into the world of particle therapy. He developed a pi meson generator facility at Stanford, which was used for biology experiments. The spirit of innovation has continued throughout the history of our department. This has included innovative treatment techniques such as the development of means to treat the entire skin with electrons for cutaneous lymphomas. There have been technological advances such as the invention of the cyberknife for treatment with precisely focused multiple high-dose radiation beams, and the use of magnetic resonance linked linear accelerator therapy, which is especially useful for treating moving targets. We were the first to exploit PET or radionuclide-directed treatment for metastatic disease using the reflection device. And now, as Dr. Lee mentioned, we're about to introduce a novel approach to the use of protons for cancer treatment, which has important applications for both children and adults. I welcome you to enjoy the time with us today, and please feel free to ask any of us questions as the day moves on. Thank you.
Thank you, Dr. Hoppe. Now I'd like to introduce Dr. Steve Atandi, who is the Lowry Krauss Jacob Director to the Stanford Cancer Institute, the Senior Associate Dean of the Cancer Programs for the Stanford School of Medicine, and the Chief Cancer Officer of Stanford Healthcare. Under Dr. Atandi's leadership, we achieved the highest designation of National Cancer Institute as a comprehensive cancer center. NCI designation requires a lot of work, lots of collaboration to develop research, advance of research, clinical and population-based research, and bring all these research into the clinical care. So with that, Dr. Atandi will share with you how radiation oncology fits into cancer.
Thank you, Dr. Lee. It's a pleasure to be here honoring this historic department here at Stanford, 70 years of remarkable scientific breakthroughs and bringing those to patients. And just imagine going from the first LINAC 70 years ago now to this miniaturized proton system that you're going to see in a short while. Remarkable history of innovation and discovery. And just imagine all the patients that have benefited from these dedicated physicians and scientists. I was trying to imagine how many patients. It must be 100,000 or more patients in 70 years being treated through these modalities and benefiting from this dedication and innovation. So incredibly proud of that. Radiation oncology, radiation therapy is one of the cornerstones of cancer therapy, as many of you know, together with surgery and systemic therapy, what we used to call chemotherapy, but now there are various types. And part of the way that we cure patients who have cancer. So, we're so fortunate to be in this period of cancer discovery, cancer science, cancer treatment, because we've learned so much about what causes cancer, the underlying causes, the underpinnings, the genetic causes, and this is translated into these types of discoveries that you're hearing now, but also immunotherapies and what we call targeted therapeutics, and just an incredible amount of discoveries that we're bringing to patients. We're super proud of all that, and we're fortunate to be working in this time. And because of all this excitement, we really have big plans for cancer here at Stanford. And that involves building a whole new cancer campus, right? So we're building a new cancer campus that's a new inpatient cancer hospital, outpatient clinics, and research buildings. And we've been working on that hard for the last couple of years, and we've been kind of in stealth mode on this. And now you're some of the first people that we're actually talking to in public about this. But we're just making the plans now, trying to find the site for this, getting the approvals from local communities, beginning to open a fundraising campaign to support this. It's probably going to be one of the most ambitious cancer plans in the entire United States. We think it's incredibly unique to build a dedicated cancer campus that is embedded within a major research university like Stanford and has these strong connectivities that radiation oncology has benefited from over the decades, right? The integration with physics and chemistry and SLAC and all these unique aspects of Stanford University. So we want to continue that connectivity while building out something that's very unique and cancer specific. So you'll be hearing more about that, and I'm happy to talk to you about that when there's some free time. So I just want to wrap up by saying what an exciting event to be part of, and what a remarkable time to be really working on cancer and bringing cancer discoveries to patients. So thank you so much. Thank you, Quinn.
Thank you. Thank you, Dr. Tondi. Now I'm going to ask Dr. Susie Hineker to come up. She will be our first speaker of the four. And Susie trained at the University of Michigan, and then we managed to snatch her over here, recruited her. She trained with us for radiation oncology, then stay on as a faculty. She's now associate professor, and her specialty is on pediatric cancer as well as lymphoma. And she's done a lot of amazing work for pediatric cancer care, so she's going to talk about that.
Great. Thank you so much, Quinn. And it's really nice to meet everybody and to be here today. I wanted to talk to you a little bit about our innovations for how to treat children with cancer and help them do it in a better way for them, and some innovations including our development of the AVATAR system. So radiation is a very important part of the treatment of childhood cancer in many cases. And sometimes kids come in extremely sick. This little baby was actually treated by my amazing mentor, Dr. Donaldson, who's here. But they can do really remarkably well and go on to live wonderful lives. Kids are tough, and it's important to give them the best treatment we can and to help them tolerate it. So we know that both the journey of treatment and that experience can affect them for their whole life. And it's important that we think about how to make this better for them. Radiation therapy in particular is difficult for children to tolerate. It's really the one treatment modality where they have to be awake and alone in a room by themselves with a large machine moving around them. And they have to be still, calm, cooperative, and maintain themselves in the treatment position, often with uncomfortable immobilization devices, and stay that way for 20 minutes a day. Can be for up to 6 to 7 weeks of daily treatment. As you can imagine, this is hard for many little kids to do. And so, as you see in this picture, many children require daily anesthesia. So that's anesthesia every day for up to 35 treatments, Monday through Friday. Can be really hard for many reasons. And one that we're just even starting to understand now is that there are bad neurocognitive effects that happen long-term related to repeated anesthesias. So this will also affect kids for their whole life. Other problems, of course, in addition to these long-term risks, are just the short-term medical risks of having that many anesthesias, the treatment burden on the family and the experience of that, and the expense on the system, the difficulty on the departments, etc. So we try to charm these kids and to do whatever we can to make them happy with us and decide that they're okay being awake for treatment. We have a little Mercedes in our department that they can drive around. We have a treasure chest. We have very talented therapists who make masks for the patients. But still, even with that, about half of kids at age 7 need daily anesthesia for treatment, a little bit less as that gets older. And then in the past, almost everybody 3, 4, 5 needed daily anesthesia. Then we started noticing a few years ago that when we were seeing kids in consult, they were in this nice, calm, quiet, cooperative state where you could do a lot of things and they wouldn't mind as long as they were staring at a screen and totally zoned out. And I also see that in my own kids. And so we had a patient around that time with Dr. Donaldson. We said, wow, he was so good when someone could hold the iPad over his head. If only there was some way we could design it so that, Sarah said, if someone could hold the iPad over his head every day during treatment, that would be just great. Of course, that's not possible, but Dr. Bill Liu, who's very genius and has great ideas, said, well, we could design a radiolucent screen that the beam could pass through. We could sort of do that. And from that, the first AVATAR system was developed, which was this paper-thin screen, a projector. The child can choose what they're watching. speaker, and we did many tests which showed it didn't significantly affect the beam going through it. This is a depiction of the first avatar, and this child is receiving treatment at this time. And the beam is just passing through the device and just making the treatment very, very tolerable for him. If anything, some of these kids, it was hard to get them off the table, mid-show, and they wanted to come back. And then his dad can just come in, then they just go home, and it's a totally different experience than the anesthesia situation. So we started presenting this work, published it. A lot of our friends and collaborators across the country were very interested, and like, how can we get an avatar? Can we buy an avatar? This is great. And the pediatric community is really collaborative. We all want things to go well for all the kids with cancer everywhere. So we wanted to figure out a way to do this. We developed a multi-center trial with the institutions listed here, 11 centers, and we prospectively examined, when they all had access to avatar, how many kids could undergo treatment without anesthesia. Also looked at anxiety and quality of life and compared it to historical controls, and found really good outcomes, that more than half of even the little tiny kids, age 3 and 4, were able to avoid anesthesia and do treatment awake when they could watch Avatar. About 80% of 5 to 7-year-olds and 85% above 8. And it worked at all institutions with protons and photons, had cost savings, and was really just like a happy study with lots of good individual feedback. That's compared to how things looked when in the past when people had no access to Avatar. So then Lisa Kim came to talk to us about it, which we can just watch a minute or so of this, and then I'll move it along.
But even more so for kids. But thanks to new technology right here at the Stanford Cancer Center, there's no anxiety. It's more like a nice, smooth ride. Let's talk a little bit about Samira's case. She's suffering from a tumor in the brainstem, is that correct?
That's right, yep. So our radiation therapists are preparing to give Samira her treatment.
So this is the AVATAR study. Tell me, what does the AVATAR stand for?
The AVATAR is a name for our audio-visual assisted therapeutic ambience and radiotherapy device.
Well, that's a mouthful right there.
It is.
What did you find with the AVATAR study?
Radiation therapy can be hard for little kids to get through because they have to be still, calm, cooperative for about 20 minutes at a time. And so that can be very hard if there's not something that they can kind of immerse themselves in or be distracted by. So that often leads to the need for daily anesthesia, which we like to avoid for a lot of reasons when possible.
So how does AVATAR make them feel more at ease?
We started to notice a few years ago that a lot of our patients were in the waiting room pretty calm and cooperative when they were watching their tablets. And we had this one little patient a few years ago who he could cooperate with a lot of the parts of setup for radiation as long as someone was standing there holding a tablet over his head. As soon as the tablet went away, he couldn't really do it. So we talked among our team and with our physicists and thought, wow, if only we could design something that was like a screen that could be there and be on during radiation.
So what did you find in the study? How much did this help with the kids' radiation therapy?
We found a significant decrease in the number of kids who needed anesthesia once we introduced Avatar. And we found 78% of them could do their treatment without anesthesia.
And what about the drawbacks of anesthesia? Why not use anesthesia and then choose screen time instead?
There are potential for long-term side effects, including neurocognition when you're doing anesthesia for like 30 days in a row. It also makes the patient families spend a lot longer at the hospital each day. It's expensive financially. It comes with a lot of associated issues like the kid has to fast, there has to be IV access. And so we know that when a kid can be calm and cooperative and go through treatment without anesthesia, it's a better experience for them and their family.
And how does it feel for you personally to see the smiles on these kids' faces, to be so at ease during radiation therapy?
I think that's just been one of the most gratifying parts. People in pediatric oncology in general are in it to make things better for the kids. And so in whatever way we can do that, whether it's better therapies or else supportive care, we want to get better from here.
So a little more screen time goes a long way.
I mean, I think so. Okay, so we've been spreading Avatar sort of around the globe where we can, and our colleagues have really taken this and used it in great ways. And this is even a 2-year-old who could do treatment awake, and then a baby in Romania who was under 1. They didn't have anesthesia ability. And so wanted to just finish by saying here our current work with this very exciting new upright proton machine, which Bill Liu will tell us more about, and we'll be able to tour and see it and describe. We plan to use Avatar for this. Our physicists also have many other inventions that they're using. Wanted to acknowledge my wonderful collaborators and say thank you. And this is a picture when Avatar goes too well. This 4-year-old wouldn't get off the table and then decided he would climb and try to see it upside down at the end of his treatment. So thank you so much, and I will look forward to talking to everybody later.
Thank you, Dr. Henniker. Next, we're going to have Dr. Anusha Kabalsi, who's coming. And Anusha trained at UCLA, and then his residency at UPenn. Then he went to UCLA on faculty, and we managed to steal him up here. And Anusha is associate professor. He's also the Marion Ellenberg Endowed Faculty Scholar. And he specializes on sarcoma and melanoma, but he's going to talk about CAR-T, because that's what his research about.
Thank you, Dr. Lei. So when I was a freshman in college, I learned about this idea that you could take a patient's T cells, one of the cells of the immune system, out of the body, design them to recognize cancer, and then give them back to the patient. And I thought it was wild. And most people thought it was wild at the time. And it turns out, though, I got into it at the right time, because within a matter of 8 years from when I first saw this in the laboratory, people were treating patients. In fact, the first patients were kids that Susie was talking about that received these types of therapies. And now they're FDA approved for patients with lymphoma, leukemia, and just in this past year for patients with sarcoma, whom I treat, and melanoma. And so my lab is trying to understand how to make these better, because this is only a small fraction of patients that benefit from this kind of therapy. And so what is this based on? And it's based on a premise that this T cell can recognize a cancer cell in the body. And I'm not sure if I can get this to play, maybe if you can practice, but this is in orange a T cell grabbing onto a cancer cell that it recognized, latching on, and then once it latches on, it injects poisonous material into the cancer cell and kills it. And it's amazing. The problem is it's a challenging operation for a T cell to completely get rid of trillions of cancer cells in the body. And so for most patients, this doesn't work. A T cell needs to get into the body of the patient, survive and expand in this new environment, find the tumor, get inside the tumor. It needs to manage a really inhospitable environment that's the tumor, that is full of toxic materials and not very rich in nutrients. The T cell needs to kill cancer cells over and over and over again to the point that it gets exhausted. And then after it theoretically clears the cancer, it needs to hang around for years to patrol and find the cancer and keep the patient cancer-free. So when I think about this, I think of disaster operations, like the fires in Los Angeles not that far ago, which is my hometown. These operations are complex, and one of the key ingredients to a complex operation is communication. So you need to be able to tell the firefighters what to do and what to do when. And if you think about this in the context of T cell therapy, it's the same. We need to be able to tell T cells what to do at different points in time and to do different functions. The key communicators in the immune system are these small proteins called cytokines. One cell makes a cytokine, communicates with another cytokine. That happens because a cytokine tells a signal to the cell. The cell is here. There's a relay to another relay, and ultimately the cell has a response. It could be to grow, to fight, to survive. One of the first cytokines that people tested in patients was a cytokine called IL-2. This is the x-rays of a patient with cancer that had spread to the lungs. After the patient gets IL-2, the cancer goes completely away. This is just a single cytokine. Incredibly powerful. What does IL-2 do? It turns T cells on, like growing like wildfire. Problem is, we've only had 2 cytokines that have been FDA approved since 1992. That's 30 plus years. Why is that? Well, cytokines make patients really sick, and we don't really know which cytokines to use when and how to use them well. And so what I propose, and what we're working on, is trying to understand the language of how T cells talk. Because if we can understand the language of how to communicate with the T cell through cytokines, we can teach them new words, we can teach them new sentences, and then we can teach T cells new stories. The idea being that if we can use this language appropriately, we can then tell T cells to not just do one thing like grow. We can tell them to get into the tumor, we can tell them to kill the cancer repeatedly, and then we can tell them to remember and patrol. And so, just as an example of this, in the green are T cells, in the red are cancer cells. They interact like this. On the right are a different cell of the immune system called macrophages. I think of them as the cookie monster of the immune system. They eat and gobble things up. And you can see that the green is eating the red, and there are pieces of the red inside the green. Macrophages do something completely different than what T cells do. But with the right signal, if you understand the language, you can get T cells to start to eat. You can make them do completely new things. And so that's what we're working on now, is to teach T cells new functions by learning their language. And we've done that with a new cytokine called IL-9, which T cells don't normally see or function through, but we've learned how to train them to see IL-9. And with IL-9, you can get T cells to do all those things that I told you about. And we have remarkable results so far showing that we can use much fewer T cells and much safer therapies to be able to treat patients with these T cells using this IL-9 system. But there's still some things that we urgently need to figure out. One is how to deliver these cytokines safely. IL-9 is one way. I think of it as using code words. You need to have code words to tell your T cells what to do without telling the rest of the body to do the same thing. You need to learn how to influence T cells, just like influencers influence people on Instagram and other social media applications, but you need a new vocabulary you need to know the jargon to be able to tell T cells to do what they need to do. And then we ultimately want to design the best cytokines for T cell therapy. And ultimately what that means is we want T cells to be able to cure cancer. We need to tell them to do all those different things that I mentioned. And so these are the FDA-approved T cell therapies and the cancers that they're indicated for: lymphoma, leukemia, myeloma, sarcoma, melanoma. None of these use cytokines except the one on the far end, which uses IL-2, which is not a very pleasant experience for patients. But what we're trying to do right now, immediately to translate to patients, is to get these IL-9 equipped T cells onto these existing FDA therapies. It's a low-hanging fruit. But in the process, we're also going to learn the language of the T cells more and more so we can fine-tune that and so we can develop the next generation. So with that, I will close. This is work done in my lab with support from the department, and thanks for your time.
Thank you, Michelle. Next, I'd like to introduce Dr. Bill Liu, who is a professor in radiation oncology. Bill received his medical degree at UC Davis. Then he did his PhD separately at UCSF and Cal Berkeley. And then he came to us to train in radiation oncology, and he stayed on. And Bill is really the master of technology, and he's going to talk about one of this here.
All right, thank you, Dr. Lei. Maybe I'll switch things up and stand over on this side. As you heard from Dr. Lei and Dr. Hoppe, we're celebrating a 70th anniversary of the invention of the medical linear accelerator by Dr. Kaplan and his colleagues. But even as we look back, really what we're looking back on is a more than 70-year history of our department and leaders looking forward and constantly inventing, and we've never stopped. So I'd like to talk a little bit about curative cancer technology of the future, but really we're starting today, and we've actually never stopped looking forward. The word that you've heard multiple times today is the word cure, which many people don't associate with cancer, but that's really what we want to focus on. And so the question is, what does it take to cure cancer? And at the basic level, it takes a couple things. First of all, to cure cancer, we need to be able to eliminate all of the cancer cells in the body, but we have to do it with the patient surviving without unacceptable collateral injury. Right? So those two have to happen together in order for us to succeed in curing. And so at a basic level, cancer can really only be cured if the treatment needed to eliminate all of the cancer can be tolerated by the patient. And so that gets to this concept that Dr. Artandi mentioned, which is precision targeted therapy. What we need to be able to do is can separate the effects between tumors and normal tissues in the body. And there's multiple different kinds of precision. One of the things that radiation therapy excels at is spatial precision. And so this illustrates kind of the difference over the last few decades in spatial precision, where older techniques to treat a tumor, in this case in the lung, the radiation dose covers the tumor, but it also damages a lot of the normal tissues, whereas with a much more focused modern treatment, the highest dose is actually in the tumor rather than out in the normal organs. And it's only with this type of precision that we can give a curative dose of radiation. That's for smaller tumors. For larger tumors, we have similar techniques to focus the radiation dose and actually wrap the dose around tumors, bend it around and away from other normal organs that we want to spare. And so we achieve this improvement in therapeutic index, or the kind of difference between tumor killing and normal tissue damage, through spatial precision. One of the advances towards even greater spatial precision is through a treatment called proton therapy, where instead of high energy X-rays, which is the current standard of care in most of our clinics, we use a charged particle or proton that that stops in the body at a specific location based on its energy. And that way, the dose can be put in a much more precise way where we want it to, and less in the rest of the body where we don't want it. And a couple of examples of how we see better focusing of the radiation dose. In this case, you can see that the high dose is covering the tumor, but with X-rays, there's lower dose that spreads out further. With protons, we're able to confine that much better. And in an example here, where we're treating the brain and the spine, you can see that a lot of the normal organs in the front part of the body that we don't want to treat are spared by proton therapy. So the challenge with proton therapy has been that it's large, heavy-duty equipment and technology. And so a standard multi-room proton therapy system that's kind of today's standard basically takes the football field to fit. Now, there are more compact systems, and they're called single-room systems that some of them could fit onto a basketball court. We have our full-court models and our half-court models. But there's still large machines that rotate around the patient to bring different angles of the beam to the patient. So one of the innovations that you'll see tonight is a new concept of ultra-compact proton therapy, where we now combine a small proton accelerator with a patient positioning system that's sort of like a chair that can have flexibility, anywhere from sitting to sort of semi-standing. And now, with this kind of more convenient, patient-friendly positioning, we can rotate the patient rather than rotate this big machine around the patient. And that allows us to bring a 3-story type of build structure into a single structure that fits within a standard radiation therapy vault. And you'll see that tonight. The room where this machine has gone, you can see it's been installed, and actually it's in a more finished state now than it was at the time we took this picture. It actually has replaced a standard radiation machine that we had. It was actually one of the first, it was the first true beam linear accelerator in the country. That was retired, and now we're replacing it with a proton therapy machine, which is unprecedented. So this will be the world's first ultra-compact system. Along the lines of precision, besides making the dose more compact, one of the challenges that we face is that we're always trying to hit moving targets very precisely. So every part of the body moves all the time. Here's an example of a lung tumor, and different strategies that we've developed over time to compensate for this motion, including synchronizing the radiation beam with the breathing cycle, or even chasing the tumor with the radiation beam. So these are what we call motion management strategies. But what this highlighted for us in terms of our thinking is, well, these are all ways of compensating for the fact that it takes longer to give the radiation treatment than for the body to move. Well, what if we could flip that around? What if we could make the treatment so fast that it's done before any motion can happen, nearly instantaneously? As it turns out, what's been shown in preclinical animal studies is that this high-speed radiation treatment, which we call FLASH, has special biological advantages too. This is an example of a study that we did where if you give a mouse radiation to the brain, it creates an inflammation reaction that lasts essentially forever, and that damages the mouse's ability to remember things and to learn and so on. And what we found was that with this FLASH type of treatment, we see much less induction of this inflammation in the brain, and that leads to improved memory function, sparing of the loss of memory that's normally induced by whole brain radiotherapy, which is something that we see in our patients as well who receive brain radiation. So the FLASH effect is less collateral damage, dose for dose, but with other studies we've seen that the tumor killing is not compromised. So that led us to kind of focus on technologies. How do we kind of create technology that can scale what we do in mice up to humans? And what that really requires is a new class of linear accelerator technology, and an invention or discovery in accelerator science was made several years ago by our collaborator at SLAC National Accelerator Lab, Sami Tintawi. This shows the first prototype, a kind of a proof of concept linear accelerator that was developed with collaboration with our School of Medicine that is intended to be the heart of a new generation of treatment technology. So this shows the current state of the art in our clinic. What we see is a medical linear accelerator that is gradually rotating around the patient to bring beams in from multiple directions. You can see it starting and stopping, synchronized with the patient's breathing. This will take about 3 minutes to deliver an ablative dose of radiation to a lung tumor, which is much faster than we used to be able to do, but still slow compared to the tumor. This is what we want to accomplish with the next generation technology that we're calling phaser, the same highly focused ablative dose of radiation completed in a fraction of a second. So about 400 times faster. That allows us to freeze the motion, make it more precise, and leverage this new biological FLASH effect, but also design it in a way that's compact and economical, because one of the critical factors in cancer therapy worldwide is lack of access to radiotherapy. And so with a very compact system that could potentially fit within, say, a cargo shipping container, that's not a totally original idea, because other things have been made to fit in that form factor, like solar power and battery storage that can be used to power emergency and disaster areas, mobile operating rooms that can unfold from a cargo shipping container. So these things exist. So if you imagine mobile surgery, power, CT scanning, and chemotherapy infusion, and add the missing element, which is mobile radiotherapy, you can imagine shipping a complete cancer center anywhere around the world in 6 boxes. So that's kind of the vision for where we want to go in the future with this type of technology. What you'll see today is the array of technologies that next generation technologies we have in our clinic today, including several world's firsts, like the CyberKnife, as you heard Dr. Hoppe mention, the PET-guided reflection system. We have the MRI-guided linear accelerator, as well as our original kind of X-ray-based linear accelerators and the ultra-compact proton therapy. And so our former chair of radiology, Dr. Gambier, had a motto that he used to like to say, invented at Stanford and used everywhere. And that kind of explains the spirit of what we like to do here. And this is just showing several of selected world's firsts of Stanford radiotherapy, including the first medical linear accelerator. That was the first patient that was treated on that machine, LA1, the CyberKnife, the ultra-compact proton, and hopefully in the near future, phaser technology as well. So with that, I'd like to thank you and move on to our next speaker.
Thank you. Last but not least, we have Dr. Max Dean, who is the Jack Lulu and Sam Wilson Professor in Radiation Oncology. Max is a Stanford lifer. I think short of undergrad, he spent his medical school, PhD training, radiation oncology residency training, and then joined faculty and now is professor. Max is expert in lung cancer and especially in liquid biopsy. So he's going to talk about that.
Great. Thanks so much, Quinn. And thank you all for coming. Sorry I was late. My little youngest one graduated from middle school just an hour or two ago, so I couldn't miss that. So I had to be a little bit late. So I'll in the next couple of minutes talk you through our work in this liquid biopsy space, and I'll explain what that is in a second. But I thought I would start with the motivation for this line of work in my laboratory, which really came from the clinic. I'm a lung cancer radiation oncologist, like Dr. Liu, and early during my when I was an assistant professor, became frustrated that we did not have good blood tests for lung cancer. And particularly the kind of blood test that I thought would be great to have is one that could tell us whether or not a patient is cured or not after we finish the radiation treatment. And so I'll give an example of two patients that sort of exemplify where this motivation comes from. These are two patients with early stage lung cancer. The patient on top has a stage 1 lung cancer. The patient on the bottom has a much bigger stage 2 lung cancer. They both were treated with focused targeted radiation we call SABR, or stereotactic ablative radiotherapy. And then we had the scan, 3 months, the first follow-up scan, where they actually both look good. The tumors shrunk significantly, and this is the expected change at 3 months. If you had asked me at this time which patient was I more worried about would likely develop recurrence, it would have been the patient on the bottom, because they had the larger tumor, of course, and the larger the tumor, the higher the risk of recurrence. But unfortunately, the patient on top is the one that recurred 3 months later. At the next follow-up scan, there were liver metastases, and so the cancer had come back, whereas the patient on the bottom, the most recent follow-up scan 9 years after treatment shows just scarring, and this patient is cured of their lung cancer. So clearly at this 3 months time point, the scans aren't good enough. They don't tell us who's likely to still harbor cancer in their body. And that's what potentially a blood test could help us with. And this leads to this idea of liquid biopsies, which really just refers to new generation blood tests that are able to very sensitively measure the presence of cancer in a patient's body and to molecularly characterize that patient without the patient's cancer without having to do a surgery or take a biopsy. And so, in particular, we've been interested for many years in something called circulating tumor DNA, and that refers to DNA molecules that come from tumor cells that end up in the blood of a patient with cancer. They're mixed together with DNA from the patient's normal cells, but just a small fraction can come from the cancer. And so when we do a blood draw, in that blood tube, we have a few molecules of the patient's cancer DNA. And if we can develop very sensitive methods to detect that, then we could have a really good biomarker, because the mutations that we look for in these DNA molecules are, of course, what causes cancer. And they're also very specific to the cancer cells. The mutations that cause that patient's cancer are present in the cancer cells, but they're not present in that patient's normal cells. And so if we could develop such tests, then we could really use these anywhere along a patient's care journey. We could use it even before a patient knows they have cancer, in what's called screening or early detection, to look for cancer. We could use it during treatment to see how the treatment's working, or after treatment to see if the treatment cured the cancer or not. And then also during certain kinds of treatments that lead to resistance, we could see what's changing in the cancer to cause that resistance. So many possible applications. So we have over the years developed a large toolbox of different liquid biopsy methods. And our first one was one that detected circulating tumor DNA, so these mutant DNA fragments from a patient's cancer very sensitively. And the first study we did with that was motivated by those two patient examples I showed you. This was a study where we had about 50 lung cancer patients treated at Stanford with radiation. And then we took blood at that first follow-up visit, and we asked how do patients' outcomes differ based on whether or not we can detect the tumor DNA in the blood after treatment. And what we found was these remarkable curves. So these curves show on the y-axis the percent of patients that are free from progression, so where the cancer has not come back. So a good curve is a curve that's flat, straight across the top would be perfect survival. A straight down would mean all the patients develop recurrence. And what you can see is there's a huge difference between the black and red curves. The red curve is the curve in the patients who had residual cancer DNA detectable in the blood, so we could still tell there was evidence of cancer. Now it's microscopic evidence. These patients had no cancer on their scan, but we could see evidence molecularly in the blood. And those patients in the study all unfortunately developed progression or recurrence. Whereas in black are the patients who did not ever have ctDNA, the circulating tumor DNA, show up in the blood and was not present that first time point. And they do extremely well. Almost all those patients are long-term survivors. So this sort of showed us that this might work. This was exciting, that the thing we had tried to do was possibly feasible. But this isn't where we want to stop. This test, this result really just says we can tell whether a patient is likely to be high risk for recurrence or low risk. But really we'd like to be able to change the outcome of the patients in the red curve to make more of those patients be cured or live longer. And so ultimately to prove that, we have to do prospective clinical trials where we use these tests. Patient gets treated, let's say with radiation or surgery, then they have the blood test, and if it's positive, if there's still cancer DNA there, we then do something about it. We treat the patient with some experimental agent or treatment. And so we have several such trials that we've launched at Stanford that are using some of the technologies that we developed in my lab, these liquid biopsy technologies, to actually now change patient treatment. And I'll give you an example of one patient on a trial. This is a patient with, again, a stage 1 lung cancer, shown on top there. This patient had surgery, not radiation. On most of our trials, we allow both surgery or radiation patients for the early stage lung cancer trials. And what's shown in orange here is how much tumor we could see on the scan. So before surgery, we saw a bunch of tumor. After surgery, the tumor is gone. That makes sense. Then the patient enrolled on our ADAPT-E trial, and we do this blood test that we developed. And the blood test showed significant levels of mutant DNA still floating in the blood, suggesting this patient was at very high risk for recurrence. And so that meant they went onto the treatment arm of the study, which means they got an immunotherapy drug called durvalumab. And that patient then got the drug, and after just 2 cycles of that drug, just about a month and a half, 2 months later, the circulating tumor DNA had gone to 0. That's the red line that went back down. So now there was no detectable circulating tumor DNA at all. We've cleared the entire detectable circulating tumor DNA, suggesting possibly that we eliminated all this patient's microscopic cancer cells. And this patient is now, this is actually a little bit outdated, the patient's well over 3 years out now without recurrence. And we think likely this patient was cured by participating in this trial and getting this drug when they had microscopic disease. Of course, it doesn't prove that. To really prove it, we have to do large studies that are randomized where half the patients get this treatment, half don't. But this is proof of concept that this could work, and we're doing more such studies. Now, as I mentioned, we've developed many different kinds of liquid biopsy methods. What I've shown you so far was all data with our first method, CAPSeq, which looks for DNA mutations. But we've developed many others, and I won't have time to go through it. I'll just highlight one other one, which is our latest method we call RareSeq. This is a different method. Rather than all our other approaches and what the field has focused on so far, looking at DNA from the tumor, this new method, RareSeq, is a blood test that looks for RNA from the cancer. And what is RNA? Well, RNA is the molecule in our cells that shows up when a gene is turned on in a cell. So if a cancer is making a certain gene, the RNA for that gene gets made. If the cancer doesn't make a gene, there's no such RNA. And so by measuring, if we could measure RNA in the blood, now instead of just saying, oh, there is cancer and we know what the mutations is, we can actually see what genes is the cancer turning on and off. And cancers continually turn different genes on and off as they're being treated and as they progress. So this could be very useful clinical information, both to learn cancer biology and develop new treatment approaches, but also for biomarker development. So this has been a very challenging problem. Others in the field have tried this and not been able to do it. RNA is very unstable. The levels are really low, so it's a technically challenging problem. So we spent over 5 years developing a method we call RareSeq, and I won't go into the details of exactly how it works. I'm happy to talk about it afterwards. But I'll just highlight a tiny bit of data from it. So one thing we did once we've developed this method, we ran a bunch of lung cancer patient samples where we had this new method, the RNA method, rare-seq, and we also had a DNA method, a commercial circulating tumor DNA method. And we compared the two and asked, hey, how do they compare? Does one pick up more cancer than the other? And what we were excited to find was that our new RNA method was able to see evidence of cancer in more patients than the already standard of care DNA methods can. That's shown here on the x-axis is the amount of circulating tumor DNA in those patients' blood. On the y-axis is how much of this RNA readout from our assay. And all those dots that are on the left, far left on the y-axis mean we found RNA, but there was no evidence of DNA mutations. Suggests that this might be more sensitive than the prior DNA methods. And indeed, if we look at what fraction of stage 1, so the earliest stage lung cancers, that we can detect in the blood with the new RNA method that's in green, it's about 30%, about a third of lung cancers. And on the red bar is the currently furthest along commercial method trying to do lung cancer screening in DNA, with a DNA approach in the blood. And that's a local company called Grail that's raised over $2 billion to develop their test. And that has a sensitivity of only about 5% in these same kinds of lung cancer. So we're very excited about this result. This is, of course, very, very early. We need to do much larger studies to follow this up. But I hope that gave you a flavor of how we are thinking about developing very technology advanced liquid biopsy approaches, biomarker approaches that can help us to both detect cancer early, but then also personalized treatment. Thank you very much.
Thank you, Dr. Dean. And many thanks again to all our speakers for their fabulous presentation tonight. But I'm sure you have a lot of questions, but because we want to keep you on time to go get the tour and to the reception, I've asked you to kind of talk to the speakers along the way when doing the reception for your questions. I think you just saw tonight just a small sample of what our research in the department is. And so I hope you agree with me that we're really poised to move forward all these innovation into cancer care. And I hope that you found the talks so inspiring tonight. Thank you.
The preceding program is copyrighted by the Board of Trustees of the Leland Stanford Junior University. Please visit us at med.stanford.edu.